Students, in this video, I will go through applying some theorems to compare angles and sides within a triangle. So in the previous video, we went over the triangle inequality theorem, which essentially just compares side lengths within a triangle and the corresponding angles within the same triangle. So what we're going to do in this video is we're going to continue that discussion and extend those ideas a little further. Let's take a look. So what I have now on the triangle on the left is triangle ABC, and I'm telling you that side lengths A, B, and C are ranked in ascending order in that manner. What are some of the conclusions that we can draw as a result of this? Well, we can certainly conclude, based on the side-to-angle relationships discussed in the previous lesson, that angle A will be the smallest angle, followed by angle B, followed by angle C, being the largest angle. And there are conclusions that we can draw as a result of this, and that is side length A will be smaller than side length B, side length A will be shorter than side length C, and side length B will be shorter than side length C. Similar conclusions can be drawn as a result of this, that angle A will be less than angle B, angle A will also be less than angle C, and finally angle B will be smaller than angle C. Similar conclusions can be drawn, okay, if we went in reverse, that if angle A is less than angle B is less than angle C, we can make similar conclusions as a result of this, that the side lengths can also be ranked in that same manner, and we can draw very, very similar conclusions. Right? This is to no surprise. So this is actually an extension of the concept that was discussed in the previous lesson regarding side-to-angle relationships. There are, and the extension is that not only can we compare what the range of different side lengths are, we can also compare the different side lengths and rank them in order according to how we see the side lengths are. I'm going to take a moment and step back and revisit an old concept that was discussed in an earlier lesson. I think it was back in Unit 1, going into Unit 2, where we talked about the exterior angle theorem. So what was discussed then was this angle on the outside, okay, as it turns out, is going to be the sum of these two angles here. Well, an extension of that idea is, well, if Z is made up of angle W and X, then it can be concluded that angle Z must be greater than its parts, right? And that's the general idea. It's that the sum must be greater than its parts, right? If I have the exterior angle in the outside, the sum must be greater than its parts. Z must be greater than W, or Z must be greater than X. Let's try to apply those concepts, okay, into a working example. So I'm telling you now that I have this triangle, ABC, and I'm telling you the side lengths of ABC. As a result of this, okay, what we're going to do is we're going to try to figure out a possible range of X. We can't really know what X is because we don't know what this third angle is based on the level of math that we know thus far, okay? We don't know what that angle is, but what we can say is, okay, we can justify a range of possible values for those two angles there. There are, of course, other methods, other means for us to actually get to the exact answer, but for the moment, okay, we don't have enough understanding to get to that point yet. Okay, so let's find out what those two angles are, or a range of possible values. So knowing this, okay, that I know that 2 is smaller than 4, which is smaller than 5, I can then conclude that angle B must be my largest angle, and angle C must be my shortest angle. Smallest angle, not shortest. So therefore I can conclude that 5x minus 20 must be greater than x. So if that's the case, then I can solve for x using my understanding of inequalities. So the inequality, remember, whenever we are dividing by a negative number, that is the only time that we need to flip the inequality symbol. But in this case here, it looks like we do not need to divide by a negative value. So the inequality symbol stays in the same direction. X must be greater than 5. And if x is greater than 5, we can then conclude that angle B, since angle B is equal to 5x minus 20, we can then conclude that angle B must be greater than 5 degrees, which isn't really saying much. I mean, like, this angle over here, certainly it looks to be an obtuse angle. However, we have no idea what the actual value is, but at the very least, we can say that angle B must be greater than 5, which is better than saying nothing at all, right? Okay. Here in this case, you're told these two side lengths. You're not told anything about this side length. What is the conclusion that you can draw as a result of this? Since these two side lengths are of the same value, then we can conclude that this is actually an isosceles triangle, and therefore the two base angles are going to be the same. X plus 20 is going to equal to 3x minus 40. We can solve for x. So therefore x will equal to 30. And if x is equal to 30, then angle L and angle M will equal to 50 degrees apiece. Okay. Let's take a look at this guy right here. And again, we don't know much about the side lengths. What we do know is there's two sides here that we're given some information about. We don't know any information about this. However, we do understand that this angle over here should equal to 60 because all three angles should add up to 180. Therefore, we can make the conclusion that angle R is less than angle Q, which is less than angle P, which then also suggests that side length R, side length R should be the shortest, followed by side length Q, followed by side length P. So what's the conclusion that we can draw as a result of this? We can then say 4x plus 10 should be greater than 3x plus 40. And based on this, we can then make some generalizations about what is the possible side length for P here. So we can say 4x plus 10 is greater than 3x plus 40, solve for x. X, therefore, turns out to be greater than 30. Since x is greater than 30, and I know that P is greater than R, and P is the longest side of the triangle, we can then get a sense of what side length P could be, right? Side length P, therefore, must be greater than 130. If side length P is greater than 130, then that means side length R must be, at the very least, smaller than 130. Okay, let's try to extend the idea even further, and this time we're going to apply the concept of the exterior angle theorem to finding out which angles are going to be smaller, greater than, or less than certain angles that are displayed. So right now I have a whole bunch of angles labeled inside of this triangle here. Angles listed from 1 through 8. And the task is to find out all the angles that are less than angle 7, and then find all the angles that are greater than angle 6. So the approach here is to come up with as much relationships as we can about angle 7 and the same about angle 6. What can we conclude about angle 7? Well, according to the exterior angle theorem, I know that angle 7 is made up of the two interior angles that are not adjacent to angle 7. So therefore, angle 7 must equal to angle 1 plus angle 2 plus angle 4. That is the exterior angle theorem. I also recognize that angle 7 is also equal to 5 plus 4 because, again, I have this triangle over here, right? So again, which triangle am I looking at? Let me use a highlighter. So, whoops. For this line, the conclusion that I can draw, why I can make that conclusion is I'm looking at this overall big triangle here, right? Where angle 7 is the exterior angle, and then the angle 1, 2, and 4 are the interior angles. And then angle 7 equal to 5 plus 4, where did that come from? Well, it came from this small triangle, right? Angle 7 is made up of 5 and 4. Okay. What other conclusions can we draw as a result of this? Okay. Are there any other angles related to angle 7? It doesn't appear to be so. So now let's try to make some conclusion about angle 6. Oh, I'm sorry. Before we get to that, let's try to figure out which angles are less than angle 7. My apologies. So since we know angle 7 is made up of these combinations of angles, we can then conclude that angle 7 must be greater than 1, greater than 2, greater than 4, and greater than 5. Right? And why is that the case? Well, that's because the sum, which is this guy here, must be greater than each one of these parts. Right? The sum must be greater than its parts. Okay, now moving on. Question letter B. Which angles are greater than angle 6? So let's take a look at what angles make up what angles involve angle 6. So I know that 6 and 4 should add up to equal to 3. Okay? Why? Because, again, angle 6 here is inside of this small triangle. So therefore, angle 3 must be the exterior angle. So therefore, 3 must equal to 4 plus 6. What's another triangle that involves angle 6? Well, it's the overall big triangle here. So the trick is to look for which other angles are within certain triangles, and then from there try to make connections. So I know that angle 6 and angle 1 should add up to angle 8, because angle 8 is the exterior angle, and then angle 6 and 1 are the two interior angles. So these are the two interior angles. So again, 8 is equal to 1 plus 6, and 3 is equal to 4 plus 6. So what conclusions can we draw as a result of this? I know that 8 will be greater than 6, or 3 will be greater than 6. And the reversal of that is 6 must be less than 8, or 6 must be less than 3. Again, the reason for this is the sum, which is this guy right here, must be greater than its part. So 8 must be greater than 6, or 6 must be less than 8. 3 must be greater than 6, or 6 must be less than 3.